Welcome to Gradient Daily. Today, we are examining a paper presented at CVPR 2024 titled Infinigen Indoors. Training an embodied AI to navigate a physical space requires millions of interactions. The core problem researchers face is that the 3D environments used to train these agents are strictly limited in number. Current state-of-the-art datasets, like Matterport 3D, rely on physical cameras capturing scans of real rooms. This manual collection process is slow, highly expensive, and yields a static set of meshes. Because the AI trains on a fixed number of layouts, it learns to memorize those specific rooms rather than learning broad spatial rules. When deployed into a real environment it hasn't seen before, the agent fails to generalize. Researchers call this the sim-to-real gap. Infinigen Indoors offers a mathematical solution to this exact problem, bypassing the physical constraints of camera scans entirely. Instead of relying on a finite catalog of data, this system functions as a procedural generation engine built directly within Blender. Look at this side-by-side comparison. Instead of treating a 3D environment as a fixed static mesh, like the object on the left, Infinigen treats a room as a mathematical distribution. It continuously generates varied shapes because the environment is coded rather than captured. To understand how this operates, we will deconstruct the three core components of the paper: the procedural asset library, the arrangement solver, and the simulation export pipeline. By shifting from static data collection to procedural generation, researchers can finally synthesize the immense environmental variance required to make embodied AI capable of surviving reality. The architecture begins with the procedural asset library. The original Infinigen framework generated natural scenes, like mountains and foliage. Translating this logic to indoor spaces required strict geometric oversight, because elements like furniture and appliances demand precise functional topology. To achieve this, the researchers applied a concept from biology, separating the genotype from the phenotype. A traditional 3D model, downloaded from an online repository, is a fixed phenotype. It exists as a single, unchangeable mesh of polygons. This diagram demonstrates the procedural alternative. The Infinigen asset acts as a genotype, a baseline mathematical formula. By moving these sliding parameter bars for height, width, and material, a single structural rule set dictates the object's geometry in real time. Tweaking these hidden mathematical variables enables the engine to output millions of structurally distinct variations from one core piece of code. Crucially, these generated items maintain physical validity. A stretched chair still produces 4 legs that touch the ground. It acts like a real object, preventing broken geometry in the simulation. This entirely eliminates the human bottleneck of manually sculpting individual 3D objects to build out training datasets. Procedural asset generation turns a single script into an endless morphological family, supplying the infinite raw materials needed to populate a simulated world. But generating infinite assets creates a new problem. The simulation is useless if an algorithm randomly places a refrigerator on top of a sofa. To prevent chaotic placement, the researchers introduced a domain-specific language, or DSL. The DSL is a specialized programming syntax explicitly designed to encode the semantic common sense of a human living space. If the procedural assets represent the raw building materials, the DSL functions as the strict local zoning laws and architectural blueprints governing how those materials assemble. This schematic maps support relationships, using glowing lines to ensure objects rest on proper surfaces. Secondly, it sets spatial boundaries with clearance limits for unobstructed human pathways. Finally, it enforces orientation constraints, dictating that a sofa must face a television. Without these programmatic limits, AI agents would navigate the generated spaces and learn incorrect assumptions about physical reality. The DSL acts as the critical bridge, forcing raw mathematical randomness to conform to the strict logical realities of human environments. The computational engine that actively enforces these DSL rules is the arrangement solver. The solver treats the process of room composition as a massive constraint satisfaction problem. You can think of this operation as a multi-dimensional game of Sudoku, where every placed object must satisfy overlapping spatial rules simultaneously. Watch the solver optimize a room. It evaluates millions of spatial configurations to find a layout breaking 0 rules. Objects clipping into each other highlight in red. The solver reorganizes the room, repelling colliding geometry until all zones resolve into green, perfectly spaced arrangements. After securing a valid layout, the pipeline moves to its final phase, exporting the mathematically perfect room into a usable format. Rendering static pictures in Blender is insufficient for this field. Embodied AI requires real-time physics simulations to accurately learn collision parameters and grasping dynamics. Infinigen Indoors addresses this by building direct export pipelines to industry-standard physical simulators like Unreal Engine and NVIDIA Omniverse. These export tools successfully convert an abstract mathematical blueprint into a fully interactive, physically grounded gymnasium for robotic minds. The structural strengths of the Infinigen framework are clear. It provides infinite data scaling combined with strict photorealism. However, the system faces distinct limitations. The first is a computational bottleneck. As room complexity and total object count scale up, the mathematical constraint solvers become exponentially slower to execute. The second limitation is the synthetic artifact problem. Even highly sophisticated procedural math currently struggles to replicate the chaotic, messy, brain-filled reality of an actual human home, like the clutter seen here. The necessary future work for this field involves taking agents trained in these generated environments and testing them on physical robots to quantify the exact improvements in zero-shot real-world transfer. To summarize the core contributions of this paper, look at this breakdown. Point 1. Infinigen Indoors provides infinite variation via a procedural Blender asset library. Point 2. Semantic rigor is guaranteed through the novel domain-specific language and constraint solver. Point 3. Immediate sim-to-real application is enabled by frictionless export pipelines to Unreal and Omniverse. If you want to keep up with the technical structures driving AI forward, like this video and subscribe to Gradient Daily for more academic deep dives. Infinigen Indoors proves that to teach machines how to navigate our reality, we must first learn how to mathematically generate an infinite number of alternative ones.